power. What is it? Well, in physics terms, we're going to be talking about power. Power is the rate work is done. And in many ways, civilization and things is determined by how much energy and how much power we can generate. So power is the rate that work is done. So power equals work over time. Joules over time in seconds. So power is going to have the unit of a watt, after James Watt, the Scottish inventor who improved the steam engine. Power can also be written as change in energy over time. Change in energy. Because after all, work is the change in energy. So what we need to know is two pieces of information: how much work is done and how much time there is. And then we can work out the power, say, of a generator. Let's try a couple of examples. How much power is required to lift a 300 kg piano 5 meters in 10 seconds. So we're going to use a winch or such to lift a piano up. So we have our piano, we run it over a pulley, we hook it up to a winch. How much power does it take to do that? Well, power equals work over time, which is equal to change in energy over time. Okay, so what do we know? We know. So what's the change in energy? If we say we're lifting it, D equals 5 meters, change in energy is going to be the change in potential energy. So EP equals mgh, which is equal to 300 kgs, 5 meters, and 10 meters per second for gravity squared. So it's going to equal 15,000 joules. 15,000 joules. So power, that's going to be, the change in energy is going to be the change in potential energy. Power, and power is a capital P, is equal to change in energy over change in time, which is going to be 15,000 joules over 10 seconds equals 1500 watts. 1 watt, just out of interest, equals 1 joule per second. 1500 watts. If we're going for an old school measurement of power, that's roughly 2 horsepower if we're using old school. Okay, let's try another one. A locomotive, like a steam train or locomotive, pulling a train travels 1 kilometre, 1,000 metres, in 50 seconds, 60 seconds. So it's doing a kilometre in 60 seconds. So it's doing a kilometre a minute, which is what, about 60 kilometres per hour. If the friction force is, let's make up a number, 8,000 newtons. So there's 8,000 newtons of friction on this train. It's a big train. What is the power required by the loco? Power required. So let's do this. So we draw a picture. We've got a locomotive got a steam funnel out the top, cab, there, pulling a thing. So we've got a friction force this way, friction force, it travels 1,000 meters that way, so D equals 1,000 meters, T equals 60 seconds, F equals 8,000 newtons. Well, what I want to do is I want to find out what is the power. So power equals work over time. So I must ask myself various questions. Do I know what the time is? Yes, I do know what the time is. That's cool. 60 seconds. Do I know what the work is? No. The next question is, can we work out, or can we determine what the work is? And the answer is yes, because work is equal to force times distance. So now the question is, do we know the force? This is 8,000 newtons. Do we know the distance? It's 1,000 meters. So yes, we can work out the work. So the work is equal to 8,000 newtons times 1,000 meters equals 8 million joules, which is equal to 8 megajoules. Okay, so the power is equal to 8. So now we feed this number, goes in there, 8 million joules over 60 seconds by 60 equals 133,333 watts. Is that a little or a lot? Does that seem reasonable to you? That's a question you should always be asking. Does that seem reasonable to you? I mean, I just did a quick conversion there, and I make that about 170, 180 horsepower using old school measurement. A loco, so it's 133 kilowatts. One of these one of these modern diesel electrics will do 1,500 kilowatts. So that's about a tenth of the power of a standard diesel electric locomotive. So that seems reasonable to me.